I want to do one more pair of videos comparing iterative to recursive solutions. This problem is a little bit different, though. This is a function that doesn't create a new list. So we saw in the previous set of videos that we were often iterating over lists and counting the elements or adding them up, or we were copying the lists or filtering them. This is a function that modifies the list that is provided, and it's called delete at index. Now, obviously, normally we don't use indexing on lists, but we can. We are allowed to decide that if I start counting from the beginning, the first index of a list is 0, and the second element is at index 1, and 2, 3, 4, and 5. My goal in this video is to write this function delete at index, which takes a list and takes an index. It goes into the list and removes the node at that index, so it fixes up the list so that that node no longer exists. And of course, that might change the index of every other thing in the list. And then it returns the element that was removed. So for example, after I run deleting at index 0 here, so I should know the delete at index function should return the element 6. That's what was in the node that was at index 0. And then the first node of the list will be the element 10 because the element 6 has been removed. That will mean that after the operation is over, the element in index 0 will be 10 and not 6. So the idea is, of course, the indexing that we're using is just whatever the indices of the elements are at that moment. And the operation that I'm performing might change the indexing after the function is over. So delete at index is supposed to take the head pointer to a list. The head pointer will be passed by reference because it might be modified because I might remove the very first element of the list. Delete at index will take the head pointer of the list and it will take the index to delete. And when the function is over, the function will return the element that was removed, the element at the index, and the list will have been modified so that that node is no longer there. In the event that the number of elements in the list is insufficient for the index that was given, we will throw the usual std out of range exception. All right, so basically, how should we tackle this iteratively? And the way I would normally view this is I would say, okay, there is still a special case. Just like inserting at the end of a list, there's still this issue, well, what happens if the thing I'm deleting is at the beginning versus somewhere else? Because when I delete a node, I have to fix whatever points to the node that I delete has to be redirected. So if I delete the node containing the 10, I have to make the 6 point to the 17, for example. So whatever node I delete, there's something that was pointing to it that I'll have to fix up. And the two main cases of that are, if the node is at the beginning, the thing I have to change is the head pointer. If the node is somewhere else, the thing I have to change is the pointer from the previous node. And so I'm going to break that down in the iterative case that way. So I'm going to begin by saying, okay, well, I guess if the index is equal to 0, that means you want to remove the first element of the list. Okay, there are two cases there. If the head pointer, actually, I might put this one first. So if the head pointer is equal to null, then I guess you can't remove anything. No index is valid on an empty list. There is no index 0 of an empty list. So if the head pointer is null, we're going to go right ahead and just throw the out of range exception right off the bat, just to get that out of the way. We may need it again later in case the index runs off the end of a list that isn't empty, but we're going to need it now. If the head pointer is null, there's nothing we can do. So I'll just say index out of range. There we go, just to make sure we don't need to worry about that special case again. All right, if the index is 0, then I am removing the very first node in the list. So you've told me to remove what is the element currently stored in the node pointed to by head. Normally when I delete things, I like to make a separate pointer to refer to the node I'm about to delete. So delete node, I'll call it delete node, and in this case it's going to be head. That way I've got some tether to the node as I adjust everything else. So in this case, I've got my head pointer. What I would like to do now is redirect the head pointer to correct the list. So I want to reconstruct the list based on this node that I'm removing no longer being there. I have a pointer to my node to be deleted, so I'm not going to lose it. So now what I'll do is I'll have the head pointer redirect to start at the next node. So that would be delete node arrow next. So head equals delete node arrow next. And because the head pointer has been passed by reference, whatever was passed in, I am allowed to just modify it. So I just say head equals delete node arrow next. And then I guess all I have to do is, I suppose, just return the element that was stored in the node I'm going to delete. So I return delete node arrow element. And in this case, in C or something, or if I were using raw allocation, so new and delete, I'd have more work to do. Remember, though, that the only pointer I currently have to this node here is this pointer called delete node, which is a smart pointer. And that means when the function ends, the smart pointer gets destroyed, and the function will automatically clean this up for me. It will destroy this node. So it'll take care of destructing the node object. There's no need to worry about a memory leak in this case. Because our lists are singly linked, there are no circular references, we can again assume that smart pointers will have our back, that they'll take care of destructing any nodes that we lose track of, that are no longer included in our list at the end of the function. Okay, so then I just do that. That, I think, is the end of the that special case where I'm moving index 0. I'll just draw this back in crudely. I wish I could be using my other program to sketch these out, but I need to have it on the same page, same screen as the code, so I get the weird crude drawing style. Okay, so I've handled the case where I'm deleting the very first index of the list. Now in the iterative case, I've got a little bit of a mess I have to take care of, which is, okay, so suppose you want to delete, let's just choose an index that's sort of inconspicuous. Suppose I want to delete the node at index number 3. Okay, right in the middle of the list. Well, I'm going to need a pointer to that node, so we'll call this delete node. I need to find the node that I want to delete. But it's not just that. So with a singly linked list, we always have this problem we can't walk backwards. If you just hand me a pointer to this node here, that isn't enough, because how do I know what came before it? The adjustment I want to make is to have the node before it point to the node after it. That means I need to find somewhere, oh, I did that thing where I pasted again. That means I need to find somewhere a pointer not only to the node I want to delete, but the pointer to the node before. I guess we can call this before node. So I need 2 pointers. Okay, well that's going to be annoying. And one of the reasons I'm sort of happy that I handled the case where I'm deleting at the beginning first is, as of line 78, we are definitely not deleting index 0. So at line 78, that means that I know that index 0 is not going to be deleted. And so here's what I'm going to try doing. I'm going to set up my 2 pointers before node and delete node to walk along together iteratively through the list as I go looking for the thing that I need to delete. So I'll start like this. I'll say, well, I know that I'm not deleting index 0. So we'll start before node here. And that means that the earliest index I could be deleting is the thing after it, index 1. So this will be delete node. And then I will just walk both pointers along in lockstep. So I'll try that. So node ptr before node equals the head pointer. And then node ptr delete node at the moment equals the head pointer arrow next, whatever comes after it. Now what I'm going to do is, I notice that delete node is currently positioned at index 1, which makes sense because I've already handled the case where I'm deleting index 0. So I'll actually keep track of what index I'm currently on. So unsigned int current IDX is 1. So I'm starting in index 1 here because I already handled index 0. Now what I'm going to do is I'm going to walk along the delete node pointer until it gets to the index I want. So if I'm deleting node 3, what I will eventually want is for the delete node to point at node 3. Every time I move delete node, I'm going to move before node along the same way. So they both move in lockstep. I'm going to use a while loop for that. I'm going to say, well, the current index is less than the actual index, or you could even say, maybe we should say not equal to make it more obvious that I want them to catch up to each other. Well, the current index is not equal to the index that I'm searching for. I'm going to walk all of the pointers along. So delete node equals delete node arrow next. And then before node equals before node arrow next. There's other ways you could do this. You could set before node to equal the old value of delete node, and then current index plus plus. And there's one more issue, which is, suppose I was trying to delete index 6, which doesn't exist. Well, then there would come a point when, I'll just redraw, I'll erase both, but I'll just redraw delete node. There would come a point when I'm on index 5. So current index equals 5. And then it says, is current index equal to 6? No. So run the loop. Okay, so delete node equals delete node arrow next. And that means delete node is now equal to null. Okay, I've obviously got a problem. I should never continue once I get to this point. So if during this loop I walk off the end of the list, that means we're just done. We might as well just stop because clearly the index I want doesn't exist. So if delete node ends up equaling null here, right after I change it, then I'm just going to quit. Who cares? There's no way I can delete a node if the list is over. So that means that I must have gone past the end of the list. So now I throw my out of range exception. I could also do this a little bit further down in the loop if I don't like the idea of splitting the loop up like this. But I have to have some way of catching, as I'm catching up to the index I'm looking, catching the case where the index I was given is way too far out. And so the index does not exist. That's where I'll do that. I'll do that inside the loop. And that means that when my loop is over, I should expect that I'm standing on the index that I want to delete. So if I want to delete index 3, 3, when my loop ends, current index will equal 3. Delete node, which is always positioned at the same index as my variable current index, delete node will be at node 3, and before node will be one node earlier. That means I now have all of the equipment that I need to be able to actually delete the node. Okay, so just like in the above case, what does that mean I have to do? Okay, the first thing I have to do is, I guess, I already have a pointer to the thing I want to delete. So the first thing I want to do is redirect from what came before it, redirect that pointer around. So just cut the node I'm deleting out of the list. So I'll say before node, arrow next, equals delete node, arrow next. Because I want it to point, in this example, at the 187, which is the thing after my node to be deleted. And then I think all I have to do now is return the element stored in the node that was deleted. Return delete node arrow element. Because just like before, in a different language like C, or if you were using new and delete, you'd have more work to do here. You'd have to deallocate stuff, but the smart pointers take care of that for me. Because delete node is now the only pointer left to this node, which means when delete node gets destroyed, the node is going to get destroyed along with it. All right, so I'm going to crudely erase this because I want to leave the diagram up and I don't want to have to redraw it when I do the testing in main, when I see whether this code actually does anything. All right, so we've got that. I'm going to fix the diagram back up to have the list we started with so that we can follow the operations as they get run in main, assuming the code compiles. So we'll save our code, we'll see whether it compiles, we'll hope for the best. It looks like it does, and now we'll run it and hope that it doesn't crash. Okay, it looks like it didn't crash. So what we'll do is we will pull this up. I'll just show off the code here. So the list contains all the same elements, 6, 10, 17, 111, 187, 116. And I'm going to perform these three operations. So I delete at index 0. And that means what I should produce is the element 6. Okay, there it is. Good. And once the deletion is over, I have a list that looks like this. So I've deleted the element with node 6, the node with element 6, and now the list's indices change because there are different nodes in the list. So I'm going to change those. So now this is index 0, this is index 1, this is index 2, this is 3, and this is 4. Okay, the next thing I do is, and so we try printing the list out, and we print out this is correct. We have the list we have in our diagram, the one we expect to see is what gets printed, so the function's working so far. We've now successfully tested the case where we're deleting at the beginning. Now I deleted index 3. Currently, this is index 3. Okay, so that means I should get 187, and I do. Good, so I get the value 187, and now we'll fix up the list. So the list should now look like this. I delete the node 187, so we'll just get rid of that completely. And then I observe that, okay, the indices have changed a little bit. Now this is index 3. The list now contains 10, 17, 111, 116. There it is. Everything still looks good. And then I deleted index 2. Okay, the current index 2 is this thing. The value is 111. Yep. And then when I perform the actual deletion, so I'll just reroute this around. And then I erase this node here. When I perform the deletion, what is left in the list, I'll update the indices, is 10, 17, and 116. That looks good as well. So there is our iterative solution to the deletion problem, modifying a list in place to delete a node. And we can see, because of the way we looped over it, we don't have any issues like we did with copy and filter in the iterative case where we're maybe running too slowly. We just had to walk along all these pointers in lockstep. This is a pretty bulky solution, though. And although I think it's easier to explain to somebody than my iterative copy or filter function, there is still a lot going on and a lot of places you could make a mistake. Even things like this. I think if you were to try and write this in one pass, it would be pretty easy to forget to throw in that if statement because it just shows up sort of in the middle of this loop. It's not obvious that's where you need to catch it. It may also not be obvious how to write the while loop. As usual, when you make a video about something, you have to sort of prepare in advance, and so it looks like I'm just pulling these solutions out of thin air. If I were given this problem and I hadn't solved it recently, it would take me quite a while to find a design that would actually make any sense. It doesn't just appear out of nowhere. And that's one reason why, if you have a recursive mindset, you often have an easier time, because the recursive solution is often a lot easier to come to than the iterative one. But in any case, here's our iterative solution. We'll write the recursive one in the next video and see what we think.